Today we're going to try to work on a confidence interval for variance and standard deviation. Um, I do want to do a little bit of intro instead of just doing some examples. And again, I'm not going to hit everything really hard, but this chi-squared distribution is what we have to use. And chi-squared distribution actually doesn't have any great shortcuts with our technology. So we have to do a little bit more math by hand. So I'll try to show you some shortcuts of how to enter this into the calculator a little bit easier. So remember, variance is how much something varies, and standard deviation is kind of the same kind of concept, but remember it's in the same unit of measurement than variance is. So remember, for a population, sigma squared is for the population for variance, and S squared stands for variance for a sample population. So for a point estimate for, sigma stands for population standard deviation, where S stands for the sample standard deviation. So again, for the most unbiased variance, we can use the sample variance as our best starting point in looking for things to vary. So what happens is we start to use this thing called chi-squared. Chi-squared is a way to help us create a confidence interval for variance and standard deviation. So remember, n is still going to be our sample size. S squared is going to be our sample variance, and sigma squared would be our standard deviation, our variance for our population. So the way this works is, as long as our sample size is greater than 1, we have some properties here. Also, for this to all work, we do have to have some normal distribution has to be involved. So for us to use chi-squared, there must be normal distribution. Just like, we had these z-scores and we had these t-scores, we had these tables, there's going to be a chi-squared table as well. And like the t distribution, the chi-squared distribution, we need to know what we call the degrees of freedom. So the degrees of freedom is the same way as we did the t. It's n minus 1. So it's going to be important to us. So again, when we do these confidence intervals, we still have this area of the curve going on. But with chi-square distributions, as we do these, they're going to skew to the right. So as we do more and more of these degrees of freedom, you kind of see it starts to become more bell-shaped curve. It starts to get closer and closer to this normal distribution, but it's not quite there. It's still kind of what we call skewed to the right. So some things we're going to work on is, the first example is trying to find these critical values. So remember, these critical values helped us create the confidence interval. And before we started using, like I said, we got shortcuts for the ones with the confidence interval with the mean, and the confidence interval for the population proportion. We got some shortcuts there because of the symmetry. But this is not going to have symmetry, so we're going to have a little bit more to do here because of that. So to find the critical values, we're going to look at this example here to start with. Find the critical values of chi-squared r and chi-squared l. So chi-squared r is to the right, the area to the right, and chi-squared l is going to be the area to the right of that, of the left side of the interval, if you will. So we're trying to find these critical values for a 95% interval, and when the sample size is 18. So to find the critical value, we're going to be using a table to do this. Now, to find chi-squared r, remember, the area of the curve is going to be 1. So remember, 95% it's got to get skewed on two ends. There's going to be a left and a right. So what we can do is, as a shortcut, is just use this formula here, 1 minus c, where c stands for the level of confidence, which in our case was this 95%. So to find the area to the right, or in other words, the critical value to the right, we're going to use this formula here. So 1 minus 0.95, if we divide that by 2, that gives us the area under the curve to the right. So again, we can use a calculator for that if we want, if I can find mine. So again, if we want to use a fraction mode, that's that alpha F1 button, number 1. I can go like 1 minus 0.95. And if I divide that by a 2, that gives me then this 0.025. So this is going to give us chi-squared to the right of the curve. Now do chi-squared L. What that is, it's the area to the right of the L. So again, we're talking about this part right here. As far as area goes, we're talking about, this is what we're actually finding, is this. So chi-squared L, it's actually not this over here. It's actually the area to the right. So when it's skewed right, this chi-squared distribution works a little bit differently because of that. So we can use the formula that they have out here. They kind of shorten it down for us. We can use this 1 plus c divided by 2 to kind of make the math work a little bit more consistent, because we don't have to do extra calculations. It kind of cuts some corners. So if I go 1 plus 0.95, if I divide that by 2, I can get that answer. Now, what we can do on our calculator as a shortcut, I think we can try to do this, is if I go up there and highlight the 1 minus 0.952, if I hit enter, it'll copy it back down for me. So what I can do now is if I move my arrow around, I can go back there and just type over the minus and put a plus there. And then I got the whole problem typed in a little bit quicker, hit enter, and that gives me now this 0.975. So it's going to be the area to the right of chi-squared L. So we have that. I think we set 0.975 there. So our critical values then we have are those. That would be our values. Now, what we can do with those values is we can actually use a table to do that. So I'll have a table that you can use as well. So if I pull that up, so to use this table, notice how we have this degree of freedom. In our problem, our sample size was, I believe, click that back over here. I believe our sample size is 18. So our degrees of freedom was going to be 18 minus 1, which would be 17. So 17 becomes our degrees of freedom. And then to find the areas under the curve that we need, the 0.975, that's going to be the L. So it's going to be, well, we actually got the 0.025 to start with. That's the right one. So 0.025 is to the right, 17 degrees of freedom. Looks like we see 30.191. So here we would say the critical value there, using the table, chi-squared r is going to be 31.191, I believe is what we said. Double check myself there. So 17 degrees of freedom, 0.05. Where was that there? 0.025, I'm sorry. So 30.191. Okay. So actually I need to change that to 0 there. So that would be our chi-squared R value. So then we have to find out what chi-squared L is. That's our left area interval, or critical value, I should say. So if I go back to my table, find that critical value for, it's like our z-score and our t-score. This is going to be our critical value for chi-squared L. So we now find the 0.975, and the degrees of freedom, I'm seeing 0.7564 as our answer there. So if we come over here, we can track down 7 point, let's make this thing work here. 7 point, where are you going here? 7.964. I did that right. Bitch, I misread it again. 7.564. Sorry about that. I'm making things easier here. Just have a really short memory. 7.564. So, before, we could start using cheats on the calculator to find these scores. Here, we're going to be stuck with the table. So that's going to be chi-squared L. That's its critical value. So we can kind of see that those are listed here as well. So we got those down. So those are going to be really important as we move forward and try to find our confidence interval. So trying to do a confidence interval, because we don't have any symmetry, we cannot use the margin of error. So we cannot use this s squared plus or minus e. So to find variance, since there's no symmetry, we're not allowed to use the margin of error. We actually have to do a little bit more work. So we have to do these calculations separately to actually find the confidence interval for variance and the confidence interval for standard deviation. So these are the formulas we got to use. We don't get to use any kind of shortcuts on the calculator per se, but we have to actually just use these two formulas to find the confidence interval for variance and standard deviation. So some things we have to find is we have to find the degrees of freedom. We may have to find the variance. If we do, we have a formula here. We will have to find chi-squared R and chi-squared L to create the critical values from the table. And then we will use these formulas here to find the variance and the standard deviation. So let's look at an example. You randomly select 30 samples of allergy medicine. The sample standard deviation is 1.2 milligrams. Assuming the weights are normally distributed, again, that's important. This allows us to do chi-squared distribution. Construct a 99% confidence interval for the population variance and the standard deviation variance. So our formula, if you see here, it's n minus 1 times s squared. So if we write that down here, we have this n minus 1 times s squared. It's going to be less than or equal to sigma squared. I'm sorry, n minus 1 over s squared over x, or chi-squared, I should say. I keep saying x, but it's chi-squared r. And over here, we have then less than or equal to then n minus 1 squared, which again is our population, I'm sorry, our sample size variance, sample variance. And we have this chi-squared L. So remember, n minus 1 is the degrees of freedom. So the degrees of freedom, well, since the sample size is 30, 30 minus 1 gives us our degrees of freedom, which is the 29. So to do variance, we need to know sigma squared. Well, they gave us a standard deviation, which again, that's, I'm sorry, we need to know, in our formula, we need to know s squared, because we won't be given the population. We will only be given the sample size. So we need to know s squared, but we do know s is going to be 1.20. So that's our standard deviation, but I can find the variance by just simply squaring the standard deviation. So if I go 1.2 squared, she gave me like 1.44. So pick up on that. So I can use this information, but I also need to know what chi-squared r is. So chi-squared r need to use our actual distribution table. So instead of making this go back and forth, let me kind of make this a little bit smaller over here. Let's see if I can find my table. So to get chi-squared r, our formula was 1 minus c over 2. So that's going to be 1 minus 0.99 divided by 2. So using our calculator, we have do alpha f1, number 1 minus 0.99, and divide that by 2. That gives me 0.005. So if I need to do chi-squared L, that's going to be 1 plus C over 2 equals. Now again, a shortcut is I can go highlight the 1 minus the 0.99, hit enter, and just go back in there and change that minus sign to a plus sign, and then hit enter, and that'll give me this 0.995. So my critical values then that I need are, I need to use my degrees of freedom as well and find that value in the table. So where's my table at? So in the table, if I use that 0.05 and I have 29 degrees of freedom, we see that we have this 52.336. So what happens is chi-squared r constant using the table itself, 29 degrees of freedom, and we said 0.05, so it's going to be that 52.336. Chi-squared L, I use the 0.995, 29 degrees of freedom, that's going to be 13.121. So then I can come along and start substituting into the formula. So I'm going to have 29 was n minus 1 times then the s squared, which is our variance for the sample, was 1.44. And we're going to divide that by chi-squared r, which is 52.336. Then that's going to be less than our sigma squared, which is not going to be less than. We're going to have this 29 times, again, the 1.44. But this time we're dividing by the 13.121. So to do this using our calculator, again, I have my alpha F1 button, number 1. So I can type in this off and just start again. That's just too much here. alpha F1, number 1. We'll do 29 times 1.44, and then we have 52.336 on the bottom. We hit enter, and that gives me then this 797. Since our numbers up here didn't go past 2 decimals, we'll probably be rounding just to 2 decimal places. So I would say 0.79, or it's actually going to be 0.80. So that's going to be less than or equal to the sigma squared. Now, instead of typing that all over again, if I use my up arrow and highlight, hit enter, that'll copy down. And then all I got to do is change the bottom. So just kind of highlight that a little bit and then just start deleting it off there. And I can turn that into a 13.121, hit enter, and that gives me then this 3.18 as our answer there. So our confidence interval, a lot of times they'll just use interval notation, so that would be 0.80 to 3.18. That would be our variance numbers with respect to this question. Now, to do the standard deviation, all we got to do is take the square of those numbers. So if I come down here and take the square root of 80, or take the square root of 0.80, and that's going to be my standard deviation. And then that's going to, then I'll just take the square root of 3.18. And that'll give me my standard deviation confidence interval. So anyway, we'll just take the square root of 0.80. So we get this 0.89. So 0.89 looks like that's what that's going to be. Is less than, and our standard deviation is less than, and I can take the square root of 3.18. So our confidence interval basically will be then this 0.89 to 1.78 would be our level of confidence in the standard deviation between those values there. So again, when you get into standard deviation and variance, you're talking about accuracy of parts and things like that. So you'll see this is more of a topic in manufacturing. So if I look at this next example, it says use technology to construct a confidence interval for the population variance sigma squared and the standard deviation, population standard deviation. Assume the sample is taken from a normally distributed population. So again, to use chi-squared, we have to have this normal distribution going on. So chi-squared again is used to find a confidence interval for variance and standard deviation. So again, some things we need to know are, one is the degrees of freedom. So that's going to be this 25 minus 1, which is going to be this 24. The next thing we need to do is find this chi-squared R and this chi-squared L. So using the table, we start with this 1 minus C over 2, which in our case, the level of confidence is this 0.95. So this is going to be 1 minus 0.95 over 2. And then we can put that into our calculator. So again, it's a fraction, so I can go alpha F1, 1 minus 0.95 divided by 2. It's going to be 0.25. Again, this math is not, I mean, if you can see it in your head, 100% take away 95% is 5%. 5% divided by 2 would be, 2.5% or 0.025. So as soon as numbers start to repeat themselves, you start to see them. So we then have this 1 plus C over 2. So in other words, we have 1 plus 0.95 over 2. So we have to, if we want to go up there and cheat a little bit, we can go up there and paste, highlight that, hit enter, bring it down, and then go in there and change that subtraction sign to an addition sign, hit enter, and that'll give us this 0.975. So we use those along with the degrees of freedom, and we use the table. So chi-squared r from our table now, so if I can find my table here, chi-squared r, we have the 0.025, and degrees of freedom is 24. So it looks like I'm getting a 39.364. Let's see if this is to work here. So make sure I get that right. 0.025 degrees of freedom is 24. 39.364. Okay. So then to find chi squared L, we have this 0.975, and we have 24 degrees of freedom. So it's 12.401. So chi squared L is going to be 12.401. So again, to find the variance interval, we have to use this formula up here. So we have this n minus 1 s squared over chi squared r. So we have n minus 1 squared chi squared r, which we have between minus 1 s squared chi squared L. So to get s squared, they gave us to us, that's 10.89, so we don't have to figure that out. That's 10.89. So remember, n minus 1 was just the 24, and then we're going to multiply that by the standard deviation, I'm sorry, the variance, which was 10.89. And then we're going to divide that by our chi squared r, which is 39.364. Again, that was just 24 times then this 10.89. And then our chi squared L was 12.401. So using our calculator, so again, I can use my alpha button, alpha F1, hit 1. So we have 24 times 10.89, and divide that by 39.364. Hit enter. So again, it looks like everything's rounded to 2 decimal places here. So we would say that's 6.64. Is our population variance. Then instead of typing that all over again, we go over and highlight that expression, hit enter, and we just need to change the denominator. So I get there and just start deleting it out. That works for me. There may be some more shortcuts. I just don't know that one yet. That looks correct. Hit enter. And we have our other end, it's going to be 21.08. So it's going to be our, so we'd have like 6.64 to 21.08 would be our variance confidence interval. So then if we do the square root of each one, that's going to give us our standard deviation. So 6 square root of 6.64 and the square root of 21.08. So if we do that, so the square root of 6.64, that's going to be 2.58. Square root of 21.08. It's 4.59. So 4.59 would be the other side of that. So my confidence interval for standard deviation would be like 2.58 to 4.59 would be how we would do that. So there's a few examples for you to kind of look at with respect to finding the confidence interval for variance and standard deviation.